Division check.
Okay, great. Yes. Thanks a lot. Yeah, maybe this way. Thanks.
Actually, there is a gesture here.
So if you just double tap, it will change to eraser. Double tap.
Okay, thanks. Yeah, so I forget my adapter, so I cannot use the computer to connect to the projector. Okay, so just to recap, what we want to do is that we want to look at expander pruning problem. So here we have a graph, right? And say that we delete some edge, a bunch of edges, and what we want to do is to prune the part, some small part of graph out, so that after deletion, and after you look at the complement of the prune part here, so you look at this part. So this part is still an expander, and the prune part is small, and by small it's just proportion to the number of deletion over 5. Yeah. So that's a problem, and we also and there is a even stronger problem where this deletion is coming one by one. But let's for now just try to look at one batch version. And so we have reduced our problem to this problem instead, where you are given a near expander, and what you want to do is to transform or to prune something out of a near expander and to make it an expander. So do you recall, so in particular we are given this, think of this as a graph. This is a set U, and it's a graph GU with some boundary, and this is a near expander. That is, every set in this is expanding, but it's expanding when you count its boundary edge, right? So you're given this thing, a near expander. And what you want to do is that you just want to prune something out again. Find a prune set, prune something out, and now say that the remaining part you prime, even without the battery edge, this part is really an expander. Okay, so I'm gonna so the problem is clear, right? We are given near expander. We want to find an expander, induced expander. Yeah. Okay. And so last time we saw that what will happen if the near expander is not already an expander, then there is something like that we will exploit. We said that if this thing is a near expander but the induced subgraph is not an expander, we said that there must exist a cut as such that the number of edges here, cut edges here, is much less than the boundary edges incident to S. Okay. So the number of cut edges here, this is C, is much less than this thing, B, from S to outside of U. Okay. Over 5. Okay, so this is just a recap. Okay, so now, so keep this in mind. If you are not done yet, then there must exist such a cut S. Okay, so now I'm gonna tell you how to certify that we are done. At least if suppose that given this near expander, if it is already the near expander, then at least there is a way to certify that that is the case. Okay. And to do that, we will really just try to solve some flow problem. And the flow problem that we will look at is this. So before I define, let me tell you some notation. So given that this near expander, given the near expander here, the U battery source function is as follows. It's just a source function where things like each of the battery edge want to send some flow. So every guy that is on the battery vertex here, this guy, it want to send some flow here. This guy should send, it has some initial source. Okay. And so this is source function where I denoted by delta U. So a U battery source function. So if I talk about 3, scale this by 3, then it just means that every battery want to send 3 units of flow. Yeah. And U sink function is just kind of similar to before. Basically, everyone in U can absorb at most its degree. Okay. And now, what we're gonna look at is this. I'm gonna say that look at the graph, this near expander, when I scale the capacity of every edge by 2/5. So the original edge here have 2/5 capacity. The battery edge here also have 2/5 capacity. Okay. So look at this graph and look at this source and sink function where every source, every battery want to send every boundary edge want to send 2 over 5 want to send 2 over 5 unit of flow out of it. So everyone here want to send this much. So every boundary edge want to saturate this boundary edge, send flow in a saturated way into the inner part. Okay. So look at this graph and this source and sink function. If there is a feasible flow satisfy this source and sink function, in the graph, after you scale everything up by 2 over 5, then I claim that we are done. Nothing to prune out. The graph itself is an expander. So that's a statement. Okay. So why is that the case? Okay, just to repeat things in other words. That is, so given a near expander, if you want to certify that like the induced subgraph is already an expander, then it suffices to just show that there is a flow in this graph such that every boundary edge can send flow at its full capacity into the inner part of the graph, and every node absorb at most degree. So let's see why this is the case. So let's prove by contradiction. Suppose that you have this flow, but suppose for contradiction that this is not the expander yet, right? So there must exist this cut we just showed, such that there must exist a cut S such that the number of cut edges here is much less than the number of boundary edges incident to S. So C is much less than B. Okay. And now, intuitively, now you should be able to see that something like this should be a contradiction already, because we say that the flow is feasible, and every guy here can send flow, but there is a cut here such that C is small. So the flow should get stuck. So there is a contradiction. Yeah. So let's try to verify this formally. So we have that F is a feasible flow in this graph. Yeah. So so given S, let's consider this cut where I include the boundary vertices here too. Okay. And you can see that the flow that can go out of S here is just at most this much. Just because there are these C many edges, each of them have capacity 2 over 5. Yeah. And now, well, the flow out must be at least like initial flow minus absorb mass, right? And there is no excess. Like usually we have that flow out is init minus absorb minus excess, but there is no excess, right? Because this is feasible. Okay. So the initial mass is what? It's just this, at least this B over times 2 over 5. And how much this thing can be absorbed is really the volume of this set. which is B. Make sense? Okay. Okay, but now I want to say that what I want to say is that this thing is small. So like you should at least, like this thing is small. So like suppose that this is not, there's nothing here, then it means that C at least B. But we have before that C is much less than B, so that's a contradiction. But this is not really like a but V can be something, but it's going to be small. How small? Well, V is at most this thing. Why is that the case?
Boundary is a boundary, so the volume V is just some
Because
volume of S.
G curly U is the near expander.
Yes. This is really because G brace U is a near expander, right? So if we consider this cut, it must expand. So B plus C is big compared to V. But how big? Like at least 5V. Yeah. So that's how we get this. So in other words, like a V cannot be too big compared to B plus C. Yeah. And now, yeah. If you want an intuition, like if C is like a very small compared to B, then this is basically V is at most like ignore the C, then V is like a 1/5B, but it means that this part is something like a 1/5B. But this implies that like a C, and this implies that the C is at least B/2. But this would contradict the whole thing, that C is small. Okay, but we don't have that C is like neglect, like, but we only have that C is less than B/5, right? So if we plug this in, then we have that, okay, instead of 1/5B here, we get that V is at most 6/5B. And by plugging it in, you still have that, like C is at least 2/5B. But this still contradicts that C is at most B/5B. C is at most B/5. So, okay. So that's a contradiction. All right, so just to repeat, if you want to certify, like this is going to be important, if you want to certify that the graph is an expander, just enough to just send flow from boundary edges in the full capacity way. Like every edge send flow at its full capacity, and each node, non-boundary node, can absorb by its degree. If you can do that, if you can find such a feasible flow, then you are done. So now we are ready to show some algorithm now. It's going to be slow, but it really solves expander pruning in one batch. Okay. How to do that? Well, just call MaxFlow on this graph, on this instance. Look at this graph, look at this source and sink function, and call push reliable or any MaxFlow really. Like if you call push reliable, just set H to be big enough. Then then you're good. So solve this flow problem. If there is no excess, you get a feasible flow, you're done, right? Now what if there is an excess? That's the only thing we need to think about. So when you have an excess, note that the algorithm here, it will give you some cut, right? Some cut here, call it P. And what do you know about this? When H is big, what do you know about what is a good property about this cut P when H is big? Yeah, like all edges that go out of this cut is saturated, fully saturated. Yeah. So that is, if you look at this cut P and you look at the flow, the pre-flow, like some excess still might be here in the in the H level, but yeah, it doesn't matter if there is an excess or not. This pre-flow on this graph is such that everything that go out of this cut is fully saturated. The flow out of P is exactly the capacity of P, the cut size of P in this graph. Okay. And also every node outside P has no excess. Yeah. So what we would have is here, right? If you have this graph here, maybe with this, yeah. And if the algorithm returns this cut P, then every guy here, excess is 0, right? So it really sends all of its flow out, which means that this thing is saturated, right? Because we said that the source here, like the source here is 205, and the capacity of this edge is also 205. So they really like saturate the flow, saturate the capacity. Also, each of these edge is saturated. Okay. So what you have here is really like, if you look at U, which is U minus P, you have some flow. Like, and if you look at F, when you just restrict yourself to this part, like let's forget about this part. This flow F really like it really just saturates this whole thing, right? So what does it mean here? It means that let's say that I define F prime to be let me say that if we define F prime to be the restriction of F into this part, then you can see that F prime is now a feasible flow. That is a feasible flow on this graph GU prime, and it really saturates all of its battery of u prime. And also the sink of u prime, like everything here still absorbed at most degree, doesn't change. So what does it mean here? It means that it should mean that the GU prime should be an expander, right? So look, like, note that, like, if you look at the G, if this is GU, okay, and look at GU prime. If GU is a near expander, GU prime is a near expander too, right? Any subset of a near expander is a near expander. And we just show that, okay, GU itself might not be an expander, but we just show that there is this flow. Like, if you just forget about this part, this flow here really saturates all the boundary edge of GU prime. And we just showed before that if for any U, if you can find this kind of flow, then it certifies that this thing itself is an expander. So just apply this lemma for U prime. Then you now have that GU prime is an expander. Does it make sense? So we really like solve MaxFlow and find some cut. Maybe you solve MaxFlow in GU and find some cut, and just forget about the part that you find a cut. Remove it, restricting everything into U prime. This remaining part of the flow turns out to be like a certificate that certifies that the remaining part is an expander. So is this clear? Okay. So we now have that, okay, find a cut, remove that cut. The remaining part is an expander. And can it just remain to say that the part that you cut must be small too. So yeah, actually, can anyone tell me why it should be the case that the part that you cut must be small? Yeah, right. So everything that you cut is fully absorbed, right? But the total amount of flow is this much. So the part that you cut cannot be more than the total amount of flow. Yeah, so that's it.
We have h equal to n plus 1 has excess, right?
It has excess, but it doesn't, like, if it has excess, that is even better, right? Like, if, yeah. Like, if there is a lot of excess, it means that there are less things to be absorbed.
Yeah.
But the thing that we cut must be fully absorbed. So, yeah. Okay, just to summarize, our goal is to find a partition P and U prime of U such that P is not too big. And if you look at the U prime part, there is a feasible flow such that all of you prime battery edge send flow at its full capacity, because that certifies that your prime is an expander. And we really get this thing. Okay. By the way, I want to note that everything above would still work if every U prime battery edge can send flow, let's say, instead of it send flow at its full capacity, which is this much, let's say it send flow like 0.9 fraction of its capacity. Then you would get that U prime is still an expander. And the reason is that we just need to look at this proof when we say how to certify that U prime is an expander, right? Well, what we do is that, okay, just compare things. If it's not an expander, then you get this cut. And if instead of, I say that, instead of saying that everyone here send 205, like each of the battery edge in this B battery nodes here can send 205. If this is like a 0.9 205, you would get some contradiction still. So nothing changed. So even if you don't send it at full capacity, but like a bit smaller, everything still works. But what if I said that like it can send maybe like 0.0001 fraction? Then this might not work anymore, right? Because we have this like we not instead of like if this is like 0.9, if I multiply this by 0.9, this still contradicts this thing. But if I replace this by 0.001, maybe like this doesn't work anymore. But you actually can try to make it work. How to do that? Let's say that each of this guy, if I say that each of the edge here, I can send alpha fraction, like if each of the battery edges here, I can send alpha fraction of flow. To get a contradiction, all I need to do is just that instead of working on this graph, I just said that I work on this graph. Like just scale everything up by 1/alpha. Then you can make it work. But maybe try to look at this exercise to convince yourself that you can like just adjust something and make it work. So the point that we really need is about actually at every battery edge can send some flow, but it must be every battery edge. Okay. So because why is it the case? Like because actually let's see. Okay. Another point is that instead of calling this basic push reliable, note that you can actually call local version of it too, because here each node can absorb by its degree, right? There is some caveat. That is, the battery node here doesn't absorb the flow, but Do you see how to fix this in the easy way?
By initializing with -1 degree.
Yeah, like let's say that you say that T here is absorbed 1, so you just set this thing to be like this thing plus 1. So, and it just really simulate what should be. Like now it satisfied the requirement of local algorithm, but really still the same. It's still about same flow problem. Okay. Okay. So I want to tell you what is wrong if we don't call exact max flow. That is like, what if h is less than n plus 1? Then you would have that, when you find, okay, if h is less than n plus 1, if there is no excess, when you